Alrighty, hello and welcome to Monday Night Office Hours. Um, as per usual, I don't have any pre-programmed material, and I am here and ready to answer any and all of your questions. So if you have them, hit me up. I'm going to start checking my email to see if any of them came through, any questions came through. But as always, I will prioritize as always, I'll prioritize any live questions. So if you're here and you need some questions answered, fire away. If not, let's see. I'll see if we have any questions over email. Hello, Lauren and Kate. Fire away. I am ready to talk some chemistry. Yeah, totally. Okay, yes, we totally can. We totally can. So here's the so there are theoretical, well, okay, so here, yeah. There are a couple ways to draw this. One of them's right. There's one correct way to draw it. If we're talking about what does the molecule actually look like? So if you look at thiocyanate, the central atom here is okay. So okay. So when I laid out the rules for building Lewis structures, I said you always pick the element that that likes to make the most bonds, right? And the thing is, sulfur. Here's the deal. Carbon. Oops. Carbon is an all-around excellent central atom because when you look at its Lewis dot structure, it has 4 unpaired electrons, and that tells you that it likes to make 4 bonds, right? Now, the catch is sulfur is third period. Which means it can break the octet rule, which means it theoretically can make more than 4 bonds, right? So when I was going over the rules of how to build a Lewis structure, I would say always pick the one that can make the most bonds. And that will guide you true. That will guide you true, almost every time, 98% of the time. Now here, technically sulfur can, make more bonds. It is capable of making more bonds than carbon. But carbon likes to make 4 bonds in almost every structure it exists, whereas sulfur, sulfur has the following Lewis dot structure. 2 unpaired electrons. Under normal circumstances, it likes to make 2. So under some circumstances, it has more, but under normal circumstances, it likes to make 2. So in this instance, you actually do roll with carbon as the central atom. That being said, I just want to be very explicit at this point in time. In an exam scenario, I wouldn't put this molecule thiocyanate on the exam because it's ambiguous. The route that you probably want to go down will actually lead you away from what the correct structure is. So I'm going to test you on, do you understand what's been communicated in class, what is conveyed in the book, and so this kind of gets into this gray area where there's a tug of war, and I wouldn't attach points to something as ambiguous as this. All right. So I don't know if that answers your question about thiocyanate's central atom. If you look at the Lewis structure, so sulfur has 6 electrons, carbon has 4, nitrogen brings 5, and the negative charge brings 1 extra 1. So we have 15 total. Once you roll with carbon as your central, we're going to attach both nitrogen and sulfur. Whoops, sorry, this is not 15, it's 16. Okay, here, sorry, hang on. Got kids in the next room. You just yelled, oh my gosh. It's way too loud. Yeah, it's okay. I'm just letting you know. Alrighty. So sorry, we have 16. You spend 4 to attach your 2 atoms to your central. Now, when you look, we can actually complete both nitrogen and sulfur's octets, right? We have 1, 2, 3, 4, 5, 6. So we can spend 6 electrons to complete nitrogen's octet, and then we spend another 6 to complete sulfur's. That spends the rest of our electrons. But carbon still only has access to 4, so we're going to have to share. And so we can take 2 of our lone pairs from nitrogen, turn that into a carbon-nitrogen triple bond. And then the last step, assigning formal charges. Sulfur has a formal charge of -1. So that's one of the resonance structures for thiocyanate. There's another one. So this is one possible resonance structure. There's another resonance structure that has, a double bond between sulfur and carbon. A double bond between carbon and nitrogen, and now in this structure, nitrogen has 2 lone pairs, and the negative charge. So you can, either one of these is pretty good. Either one of these is acceptable as a correct answer. Nitrogen is, I believe, more nitrogen's more electronegative than sulfur. So this one is favored from that perspective because it puts the negative charge on the more electronegative element. But honestly, both of these are widely accepted. All right, let's see. Are formal charges minimized when there are less charged values? Great question. Let's take a look at that azide ion, which is azide is the name of the N3 with a negative charge anion. So when you draw the Lewis structure for azide, there are a couple different ways that you can draw it. There's no way around having a total of 3 formal charges on this molecule. Because that nitrogen in the center in all of the best resonance structures has a charge of +1. You can, however, draw a couple resonance structures, one in which the nitrogen on the very left is triple bonded, and then the nitrogen on the right has a charge of -2, and then there's another resonance structure where you can draw the nitrogen on the right with a triple bond. And the nitrogen on the very left with a charge of -2. And then the central one still has that formal positive. All right. So, all of these resonance structures are more or less equivalent. And when I say more or less, they there's one that's slightly better, but they're all accepted as equivalent. There's one that's slightly better, and I'll talk about the reason why. First, let me talk about why they're all basically the same. They're all basically equivalent. So all of these, we've got the octet rule taken care of. So octet rule, check. Minimal formals, minimal formal charge, check. Negatives on electronegative elements, Yeah, all the elements are the same, so of course that one's gonna check out. So we got to check there. There's one that is slightly better, and that one is this guy. And again, this is a kind of a nuance that I didn't explicitly teach in class, so of course I wouldn't test on it. But the reason why this one's better is, given a choice, it's better to have negative charges, 2 -1s on 2 different nitrogens, than to have both negatives on the same. So this is not as good, and this is not as good. As this. It's better to have them on 2 different atoms. And the simple reason why is because like charges repel each other, right? Negative charges repel negative charges. So given a choice, the electrons, the extra charges, would rather not be bunched up around the same nucleus. They'd rather be on different nuclei. They'd rather have room to breathe. Kind of like when we were doing orbital diagrams, and the electrons would occupy different p orbitals before they double up in a p orbital. It's the same kind of idea. So the one that I boxed in yellow is the best one, because if you have a choice, you'd rather have two -1s on different nitrogens than a -2 on one nitrogen. But again, it's a level of nuance that I would not test for. Awesome. Okay, let's see. All right, chapter 9. Let's take a look. Sorry, I gotta log into my textbook. All right. All right. All right, starting with 70. Oh, sorry, not chapter 10. All right, so this is number 70. Oops. Eric, I haven't set a due date for it. As of lecture this afternoon's lecture, we covered all the material that you need to be able to answer the questions on exercise 5. I haven't set a due date for it yet. The latest possible due date would be the day of the final, but I don't want things to pile up too hardcore. So yeah, I'm sorry. I don't know at the moment. I'm currently scheduling wise trying to figure out when to set exam 4. So once I get that, then I'll be able to turn. Once I get that, ironed out, I'll be able to turn my attention elsewhere. Okay. This one's cool. So, with this one, problem 70 is draw the Lewis structure. Oh, no. I totally. Eric, I totally wouldn't do that to everyone on the week of Thanksgiving. If anything, I might set it for next week, but I might push it back further just because it's, I don't want to put everybody in too much of a bind, if it can be avoided. So in problem 70, we're supposed to draw the Lewis structure for methyl azide, which has the chemical formula. Where did that go? Here we go. CH3N3. And here's the cool thing. Then it says for each resonance structure, assign formal charges to all atoms that have formal charges. Now here's the thing. And this one's cool. This is more of a this is an organic molecule. And here's the fun part about this problem. There is no central atom. All right, there's no central atom. Now, the idea of a central atom is something that we teach in general chemistry because it's helpful. It gives students a place to start. And many of the molecules that we look at and we're studying in general chemistry have one. The thing is, outside of general chemistry, the idea of a central atom becomes less and less useful. It becomes less and less useful because it becomes less and less common. Most molecules do not have a central atom, and in fact, almost all organic molecules don't. So we're still gonna calculate our electrons like we do for any Lewis structure, but instead of picking a central atom, we are going to just attach all of our main atoms in a string, so to speak, in a chain, and then figure out a way to solve the problem of completing everyone's octet. So let's get to work. We have one carbon. Hydrogen has one electron, but we have three of them, so that'll bring 3. Nitrogen has 5 electrons. Oops, not 5. Nitrogen has 5 electrons, but again, we have 3 of them. So that'll bring a total of 15. So 15 plus 3 is 18. 18 plus 4 is 22 electrons. So, okay, so here, we're going to make a chain out of our atoms, at least the bigger ones that like to make more than one bond. So this will cost 1, 2, 3. We made 3 bonds, so this will cost 3 times 2 is 6. And so this would be 16 electrons. We got to attach our hydrogen somewhere. I'm going to put them on carbon. That'll cost 2, 4, 6, another 6 electrons. All right. Let's start completing some octets. That nitrogen there on the end. it has access to 2 electrons. It needs 6 more, so let's give it 3 lone pairs. Now the nitrogen in the center has access to, or not in the center, but the one next to the terminal nitrogen needs 4 more, right? So let's give it 2 lone pairs. That'll complete its octet, but it also taps out our electron bank, right? We have no more electrons to spend, and this nitrogen needs 4 electrons. Right, so we're not quite done here. That needs 4 electrons, but we've seen situations like this before. When you're out of electrons in your budget, but you still need to complete octets, that's where we turn to multiple bonds. So we're going to take this, make it a nitrogen-nitrogen double. All right, now the one nitrogen still needs 2 more, so we're going to do that again. And at this moment in time, we have a complete, everybody has a complete octet. Everyone has a complete octet, but we don't know yet if this is the best resonance structure because we haven't assigned formal charges yet. So let's take a look at this carbon. Carbon, when it's neutral, has 4 electrons. When you calculate formal charges, you get 1 electron per bond plus all the lone pairs. This carbon has 4 bonds, so we have a formal charge of 0. Let's look at this nitrogen. Okay, sorry, Kate, I just saw your comment. I was able to draw this with 2 nitrogen doubles, 1 single. Yeah. So I'm not done with this structure, but I'm just assigning formal charges, and then we'll go from there. Because I believe, yeah, there's a better resonance structure, and we'll get there, but we're just looking at what we have on hand right now. So nitrogen has 5 electrons when it's neutral. In this structure, it has 4 bonds, no lone pairs, so 5 minus 4 is a positive 1. And you'll notice this nitrogen has the same scenario. 5 electrons when it's neutral, 4 in this structure, so it has a charge of positive 1. Finally, let's do this nitrogen. All nitrogens, when they're neutral, have 5 electrons. In this structure, it has 6 electrons in lone pairs plus 1 in its bond. 5 minus 7 is negative 2. So in the structure that I have drawn, we have 2 positive 1s and a negative 2. All right, now we can definitely minimize our formal charge. Let's talk about how. I'm going to redraw the structure that I had. So watch what happens when we take one of these lone pairs on this terminal nitrogen and turn it into a multiple bond here. Now, we can't do that without changing the number of bonds to that nitrogen, because this nitrogen has 4 bonds already. it can't make a new bond unless we break a bond that it has already. So we're going to take this triple and turn one of those bonds into a lone pair on this nitrogen. Now watch what happens in this resonance structure. Now this nitrogen on the very end took a lone pair, used it to make a double bond with the nitrogen next to it. Now this nitrogen here lost its triple bond, and now that triple bond is a lone pair there. All right, so this is a resonance structure. Let's see if we've been able to minimize formal charges. So carbon we don't have to calculate because it hasn't changed. If you look at this nitrogen, when it's neutral, nitrogen has 5 electrons. In this structure, it has 2 electrons in lone pairs plus 3 bonds. 2 plus 3 is 5, which means it will have a formal charge of 0. Let's look at this nitrogen. Again, 5 when we're neutral. It has 4 bonds in this structure, so 5 minus 4 is positive 1. Looking at this nitrogen on the very end, neutral when it's neutral it has 5. In this structure, the nitrogen on the very end has 4 electrons in lone pairs plus 2 bonds. 5 minus 6 is negative 1. So we will have a charge of negative 1. Oops. Negative 1 on the very terminus, and a positive 1 in the center. There's actually one more resonance structure. One more resonance structure we can draw. We can take another lone pair from this one, turn it into a triple. If we do that, then we have to break another bond to that central nitrogen because it cannot have more than 4 bonds. This will give us a Lewis structure that looks like this. Now the nitrogen on the very end is triple bonded, whereas the nitrogen attached to carbon has 2 lone pairs. And when you calculate formal charges, the nitrogen kind of in that center still has a positive 1, but now the nitrogen with 2 lone pairs has a charge of negative 1. Now when it comes to which one is the best resonance structure, either of these will work. These are equivalent resonance structures. They're the best because of their minimal formal charge. So those are the 2 best resonance structures for this molecule. Now, something that I should point out is, no, this is what the molecule actually looks like. They mentioned this was methyl azide. But for this chemical formula, this is not the only Lewis structure you can draw. So if your carbons and nitrogens were arranged in a different fashion, that's totally fine. Because as you'll learn in organic chemistry, a molecular formula, there are many different molecules that all share the same molecular formula. So one molecular formula can correspond to multiple structures. This happens to be one of them. All right, let's see. 73B. Okay. And with 73, these are ones where they're explicitly warning us the octet rule is not followed. Oops. 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 Where did that go? There we go. So, let's see, 73B and 74B. Yes, they are very similar. Kate, there are some very rare examples where nitrogen does break the octet rule by having fewer than 8 electrons. That being said, the fact that it's breaking the octet rule actually tells you something about the molecule. It's very unstable. We know the reason why the octet rule is a thing is because it's based on the stability of the noble gases, right? So if you have a molecule where you have nitrogen and it has fewer than 8 electrons, that molecule is going to be unstable. It's going to be very reactive because nitrogen is desperate for one more electron. It'll do anything to hit that octet rule, and so it reacts violently often. All right. Let's take a look at number 73. So 73B. Now we're drawing the Lewis structure for NO2. So nitrogen, 5 electrons. Oxygen has 6, but we got 2 of them. So it'll bring 12. So there's 17. Yeah, totally. So central atom, we're going to pick nitrogen because it likes to make more bonds than oxygen. The cost of attaching. Both oxygen atoms is cost 4 electrons. Now we've got an oxygen that needs 6 more. Actually, when we stop and looking at it, both oxygens need 6 more electrons. Leaving only 1 electron that we can give to that nitrogen. Now, it does not matter what you do. So right now nitrogen has 5 electrons. The best we can do is grab a lone pair, use it to make a double bond, and take that lone pair electron, use it to make a double bond. But still, you'll notice that this nitrogen has 7 electrons, right? If you try to steal an electron from one of the oxygens, possibly move it over, like for example, if you took one of the electrons from this oxygen over here to complete nitrogen's octet, it creates another problem. Oxygen now only has 7 electrons, right? And the thing is, this one is the better resonance structure. Oops, there we go. This is the best resonance structure because oxygen is more electronegative than nitrogen, and so we would rather give we'd rather have an element that's less electronegative, break the octet rule, than the one that's more electronegative. Yep, yeah. But you already knew that. The one last thing we do have to do here, though, is we do need to assign oxidation states. I mean, not oxidation states, formal charges. So if you look at this oxygen, oxygen has 6 electrons when it's neutral. In this structure, it has 2 bonds plus 4 electrons in lone pairs. 6 minus 6 is 0. Looking at this nitrogen in the center, nitrogen has 5 electrons when it's neutral. In this structure, it has 3 bonds and 1 electron. In a quote-unquote lone pair, it's not really a pair, but it has 4. So this nitrogen has a formal charge of +1. And then this oxygen, 6 electrons when it's neutral. In this structure, it has 1 bond, 6 in lone pairs. 6 minus 7 is a -1. So nitrogen will have, a formal charge of +1, oxygen a formal charge of -1. Okay. So that's 73. B, Kate, you've already noticed the similarity with 74. B. So this Lewis structure just has nitrogen and oxygen. Nitrogen brings 5 electrons. Oxygen brings 6. We've got 11 electrons to spend. Our first 2 we're going to spend on a nitrogen-oxygen single bond. Our next 6 we'll spend on completing oxygen's octet. We only have 3 electrons left, and we're going to spend them on nitrogen. Now, we still need to try to complete its octet. So let's take one of our lone pairs off of oxygen, turn it into a double, and that's as good as it's going to get. When you calculate formal charges here, oxygen has 6 electrons when it's neutral. In this structure, it has 2 bonds, 4 lone pairs, 4 electrons in lone pairs. So that's 6 minus 6 is 0. When you look at nitrogen, nitrogen has 5 electrons when it's neutral. In this structure, it has 3 electrons plus 2 bonds. So that's 5. 5 minus 5 is 0. So this is no charges necessary. Excuse me, sorry. No formal charges in this Lewis structure. All right. So that is 74B. Oh, how about we do 74 C? All right, 74 C. We need to draw the Lewis structure for ClO2. Chlorine brings 7 electrons. Oxygen brings 6, but we got 2 of them. So there's 19 electrons. Chlorine, third period, can make a lot of bonds. So we're going to start by picking that as our central and attaching our 2 oxygens to our central atom. We've got 2 oxygens that need 6 more electrons each, so that'll be 12. We have 12 in the budget, so I'm just going to throw them all up all at once. (15 minus 12 is 3. We're going to give all 3 of these to chlorine. And you'll notice chlorine has 7 electrons. All right, chlorine has 7 electrons. Now, it can break the octet rule. And so we're going to break the octet rule by going above, because going above is better than going below. All right, now let's go ahead and calculate some formal charges. 6 when it's neutral. In the structure, we've got 4 electrons and 2 bonds. 6 minus 6 is 0. 7 electrons when chlorine's neutral. In this structure, it has 3 electrons plus 3 in bonds. 7 minus 6 is a positive 1. This oxygen, when it's neutral, oxygen has 6. It has 6 electrons and 1 bond. 6 minus 7 is negative 1. And so this would be the Lewis structure for chlorine dioxide. All right, and that is number 74. C. And then I accidentally wrote that in the wrong layer. So I gotta rewrite some stuff. Okay. Next is 77. B. Okay, so we have, oh, interesting. I 3 minus. Okay, so iodine has 7 electrons, but we have 3, so 3 times 7. Oh, hang on. That's not it. Plus we have the negative charge. Which brings 1 more electron. So 3 times 7 is 21. Plus this 1 electron is 22. Okay. So iodine is going to be our central atom. We are going to spend 4 electrons to attach our 2 other iodines to our central. Oh, sorry, Kate. I just saw your question. Hang on, let me dial things back. Oh, you know what? Kate, you are totally right. Oops. You can make another double bond, and if you do, it'll actually minimize our formal charge, making it a better resonance structure. Because this has no formal charges, much better resonance structure. So well done there. Yeah, that is the Lewis structure. Sorry, I was just on autopilot. I totally missed it. All right. Jumping back to the triiodide. So we have a we have an iodine that needs 3 lone pairs, right? Oops. All right, that will leave us with 12 electrons. On the other side, this iodine needs 3 lone pairs. All right, now that iodine in the center needs 2 more electrons to have a full octet. Now here's a problem we haven't run into before. We have 2 electrons left. What do we do with them? What do we do? Um, so with these two electrons, so everybody's got a full octet. Everybody's got a full octet, but we still have to place them. So we're going to give them to iodine. Because iodine can break the octet rule, right? It's allowed to have more than 8 electrons. So we're just going to pop them on there. Now, when you calculate your formal charges, the iodine on the edge, iodine has 7 electrons when it's neutral. In this structure, the green iodine has 1 bond plus 6 electrons, so that's 7. 7 minus 7 is 0. And you'll notice the salmon iodine has the same situation going on. But the iodine in the center... Kate, great question. The answer is no, and I'll show you why. Well, originally they can be, but they have to end on the middle one, and I'll show you why in just a second. First, let's assign our formal charges. When iodine is neutral, it has 7. In this structure, it has 6 electrons plus 2 bonds, which is 8, giving us a formal charge of -1. So, in this structure, we have that formal charge of -1. Now, Kate, let's investigate what would happen if we put the extra pair on one of the terminal iodines. Theoretically, you could. There's at least on first pass, nothing particularly wrong with doing it. So let's just throw it on this guy here on the end. Now, when you calculate formal charges, this iodine on the very end, 7 when it's neutral, 7 in the structure, formal charge of 0. Let's calculate the formal charge for our central iodine. 7 when it's neutral. In this structure, it has 4 electrons plus 2 bonds. So 7 minus 6 is +1. And now for this terminal iodine, we've got 7 when you're neutral. In this structure, it has 8 electrons plus 1 bond. So 7 minus 9 is a -2. So even though you could give it to one of the iodines on the end, because any iodine could break the rule, in this resonance structure, we end up with a formal charge of -2 and a formal charge of +1, whereas if you give the central iodine the lone pair, it minimizes formal charge. So that the reason why the central iodine has to take the lone pair for this molecule is because that is the one that results in formal charge being minimized. Totally. If that weren't the case, you could put it on any iodine if there wasn't that formal charge situation in play. Because all iodines are the same from the standpoint of they can all break the octet rule. But in this specific structure, the only way to minimize formal charge is putting it on the central. All right, let's see. Okay, we're also doing 77D. Hope that's B. All right, let's. For 77D, we need to do Germanium tetrafluoride. I feel like germanium, I think germanium has 4 valence electrons, but let's just take a look. Sure does. Germanium is right here. 4th column in the main group. So it has 4 valence electrons. Fluorine has 7. But we have 4 fluorines, so 7 times 4 is 28. $32 total. We're going to begin by placing germanium at the center, because it can break the octet rule. And we are going to attach all of our fluorines to our central, spending 8 electrons. Yeah, totally. Germanium is a main group metal. All right, we've got 24 electrons left. Fluorine needs 6. 6 electrons to complete its octet. We have 4 fluorines, and 6 times 4 is 24. So we actually have enough to give each fluorine a full octet. All right. So this is the Lewis structure with completed octets. Next, we need to check our formal charges. Oh. All right, so if we calculate the formal charge for fluorine, fluorine has 7 electrons when it's neutral. In this structure, it has 6 electrons plus 1 bond. So 7 minus 7 is 0, and you'll find that that is the case for all of these fluorines. Now let's look at germanium. When germanium is neutral, it has 4 electrons. In this structure, it has 4 bonds. So formal charge of 0. So this is the Lewis structure. For germanium tetrafluoride. All right. That is 77D. All right, let's take a look. 79 through 84. All right, 79. Order these compounds in order of increasing carbon. Okay, let's see. We haven't gotten to this stuff yet. Let me see. So I'm just looking at through 84. Ah. Oh, yeah, yeah. Oh, hey, Eric. Sorry, I just saw your comment. Let me boot up that lab stuff. Okay, let's see. You want to know about data analysis question 4. Okay. So first off, one of the things that you should be aware of is the value that you're going to get here will be very small. So the fact that it's 10 to the negative third is not alarming in and of itself. Excuse me. I'm so sorry. Okay. I just had to get that yawn out of my system. Oops. There we go. So, let's talk about the data analysis for Lab 9. So step 4 is converting the ISE reading from milligrams per liter to molarity. All right. So what we're doing here, what we're setting up is we have some quantity that is in milligrams Okay. So let's just let's walk through this one step at a time. And we'll see if maybe there's something awry. So the deal is the ISE reading is in milligrams of calcium per liter, and we want to convert it to molarity. Now, molarity is moles of calcium per liter. So one of the things that you'll notice is your denominator is the same. Right, it starts in liters, ends in liters. It's your numerator that changes. So the numerator is where the conversion has to happen. All right. So I'm just going to make up an ISE reading. Let me pull up. Excuse me, sorry. All right, I'm just going to do one that's like ballpark in there. I'm going to do, so let's say that we have an ISE reading of 197 milligrams of calcium per liter. All right. Here's how you do the conversion. So we want to get to moles. And ultimately, what we're going to use is the periodic table because that tells us how many grams of calcium are in a mole. But before we can get there, we need to convert from milligrams to grams. So we throw milligrams of calcium in the denominator, grams of calcium in the numerator, and 1 milligram of calcium is 10 to the negative third grams of calcium. So milligrams cancel. The next step is we need to convert from grams of calcium to moles. And this is where we use the periodic table. So I believe, let me bust out my periodic table. I think it's like 40.08. Yeah. Calcium, 1 mole of calcium has a mass of 40.08 grams. All right. So now that we've converted to moles, we're ready to crunch our numbers. We've got 197 times 10 to the negative 3 divided by 40.08. Hang on, I messed that up when I was punching it in. 40.08. All right, there we go. So we can keep 3 sig figs from our 197. So this will be 0.00492. This is moles of calcium per liter, or 4.92 times 10 to the negative third moles of calcium per liter. Yeah, and Eric, here's the deal. So I have the so I was just looked at all the ISE values. I picked one that was around what everybody's is, and everybody should be getting for their ISE conversions something times 10 to the negative third. So that's totally normal. Sorry, let me see. Maybe I don't actually know off the top of my head what the ballpark values should be. Let's see. I'm just looking at the data here. If we go. -5, 3. Times let's see. Okay, so I just, from looking at this data, it's possible that that's where mistake lies. Let me. So here's I guess here's my question. So Eric, and I don't know for sure. Let me just take a look at the group you fell in. Yeah. Um, so Eric, question. When you calculated your molarity for or when you calculate the moles of calcium plus magnesium. So this is the setup. You have your milliliters of EDTA, and then you multiply by the unit conversion to convert milliliters to liters. And then you multiply by the molarity of EDTA. And then finally, there's a 1-to-1 mole ratio between the moles of EDTA and the moles of calcium plus magnesium. So the molarity of EDTA is given. This guy is 0.010. My question for you lies right here. The milliliters of EDTA used to get this value, you got to go this is equal to the final volume minus the initial volume. Okay. Okay. No, that's good. That's good, actually. Eric, that's spot on. Right, so you got moles of calcium plus magnesium. You calculated them as 0.976 times 10 to the negative 5. This is moles. But before we can do the subtraction thing, we got to take this to molarity. Right, so the molarity of calcium plus magnesium is equal to the moles, which you calculated, 9.76 times 10 to the negative 5 moles, over, now the volume here is the volume of hard water, which we're told that we use 10 milliliters of water, which we've got to convert to liters. So that's what goes in the denominator here. And when you punch this into your calculator, you get 9.76 times 10 to the negative 3 molar, for calcium plus magnesium. Right, so this is the molarity of calcium plus magnesium. Ah, there it is. That's where the problem lies. And that would make total sense because you divided by a number that was smaller. Yeah, man. I'm glad we got to the bottom of it. It's usually some weird little quirk like that too, you know? It's always super satisfying though when you can finally put your finger on it. Fluorine, I absolutely could. Yeah, totally. So the thing is, um, let's see. Okay, the Lewis structure. So it doesn't really matter um, where you put the F's in the Lewis structure because the Lewis structure does not reflect the three-dimensional shape of the molecule. So we're going to start by totaling our electrons. Sulfur brings 6. Fluorine brings 7, but we have 6 of them. And 6 times 7 is 42. 42 plus 6 is 48. So we start with sulfur as our central atom, and we need to attach all of the fluorines to the central. This is going to cost 2, 4, 6, 8, 10, 12. Leaving us with 36. Now, each fluorine needs 6 more electrons, and we have 6 fluorines. So 6 times 6 is 36. There are 36 electrons left in our budget. So we have enough to give each fluorine 3 lone pairs. When you look at formal charges, fluorine, when it's neutral, has 7 electrons, and in this molecule, this fluorine and each other fluorine has 6 electrons plus 1 bond. So 7 minus 7 is 0. When we calculate it for sulfur, sulfur, when it's neutral, has 6 electrons. In this molecule, sulfur has no electrons but 6 bonds, so you get 1 electron per bond. 6 minus 6 is 0. So this is the Lewis structure for fluorine. Yes, correct. Placement does not matter for Lewis structures. Alrighty. That brings us to 10 o'clock. Thanks to everybody who came out, participated live, and those of you who are watching later. Thank you as well. I will catch you all in lecture on Wednesday. Later.